One German operator was asked to send the message again and chose the one setting he was never supposed to reuse. That decision lasted only minutes. Its consequences ran for years. On the 30th of August 1941, British listeners caught two long German teleprinter transmissions produced from the same Lorenz starting state. The second transmission was not an exact copy. The operator shortened words, changed parts of the wording, and introduced enough differences to expose something Bletchley Park had been waiting for: two related plain texts covered by the same cipher stream. This was not the moment Britain simply read Lorenz. First, John Tiltman had to separate the two German texts. Then, Bill Tutte had to do something stranger. From the recovered cipher key, he inferred the logic of a machine that nobody at Bletchley Park had ever seen. That work opened the route to Tunny, Heath Robinson, and eventually Colossus. The scale matters because Lorenz was not a field cipher used for routine platoon traffic. It protected strategic teleprinter links used by German high command. The National Museum of Computing describes roughly 30 high-frequency Lorenz links across occupied Europe and estimates about 200 machines existed during the war. The British name for the traffic was Tunny, one branch of the wider fish family of non-Morse signals. So the famous error was more than a careless repeat. The dangerous combination was reuse plus revision. If the operator had retransmitted the message by the book, or even repeated the first text with perfect mechanical fidelity, the opening available to Tiltman would have been 3 radically smaller. The incident worked because several things lined up at once: a long message, a repeated starting state, closely related plain texts, and British cryptanalysts who already understood what a reused additive stream could expose. That distinction also answers a larger historical question. One operator did not crack Lorenz in an afternoon. He created the rare sample that made a much deeper attack possible. The reason becomes clear once you see what Lorenz was designed to do. Lorenz solved a communications problem that Enigma did not solve well. Enigma was portable and widespread, but long messages still had to be enciphered letter by letter and then transmitted, usually in Morse. Senior headquarters wanted fast traffic that could move directly through teleprinters across long radio links. The Lorenz SC family sat between a teleprinter and the radio circuit. A teleprinter represented each character as 5 binary impulses, giving 32 possible 5-bit combinations before shift codes could be used to cover letters, figures, and controls. Lorenz generated another 5-bit pattern and combined it with the character before transmission. At the receiving end, a machine set the same way generated the same pattern again and canceled it, restoring the original text. In modern terms, the operation resembles XOR, although the wartime operators did not need that vocabulary to use it. The two ends therefore had to agree on the wheel state before a transmission began. A wrong start did not produce slightly damaged German. It produced nonsense. The security came from the key stream. If every message began from a fresh setting and the generated stream remained unknown, an interceptor saw only apparently meaningless 5-bit traffic. Lorenz used 12 wheels, divided into 5 chi wheels, 5 psi wheels, and 2 motor wheels. The National Museum of Computing gives about 1.6 billion possible starting positions for those 12 wheels. The Bill Tutte Memorial Fund also notes that the internal pin patterns on the wheels could be changed, adding another layer beyond the message start. That made Lorenz suitable for high-grade strategic information. Its traffic linked German command centers and carried the sort of material that becomes dangerous when read quickly: operational assessments, orders, movements, and reports intended for senior staffs. Bletchley Park later decrypted more than 13,000 Lorenz messages between late 1942 and the end of the war, according to the General Report on Tunny figure reproduced by the Bill Tutte Memorial Fund. But the design depended on procedure. A stream cipher can be very strong while still being vulnerable to a reused stream. If 2 different plaintexts are combined with the same key stream, combining the 2 ciphertexts cancels the secret stream and leaves a relationship between the 2 original messages. Cryptanalysts called such a pair a depth. A depth did not automatically reveal German. 2 unrelated messages under the same key could still be extremely difficult to separate. The sum tells you how the texts differ, but not which side owns which letters. Without strong linguistic clues, the possibilities multiply quickly. What happened on the 30th of August gave Bletchley Park something far better than 2 unrelated texts. It gave them 2 versions of almost the same message. 4. The message itself was long, close to 4,000 characters. In a later recorded account, John Tiltman says the plain text proved to be a report for the German military attaché in Athens about the situation on the Russian front for the 29th August 1941, ranging geographically from the Odessa area toward Finland. That detail matters because the sender was not retyping a greeting or a short administrative note. He was re-entering pages of high-level traffic by hand. On the first transmission, the sending operator set the Lorenz system and sent a 12-letter indicator telling the receiving end how to align its machine. The message then ran thousands of characters at teleprinter speed, but the plain text still had to be keyed by a human operator. Somewhere in the chain, reception failed badly enough that the other end asked for the whole thing again. There was no convenient digital file to resend. The sender had to type the report again. Athens, 30th August 1941. The operator has already keyed nearly 4,000 characters once. The return request comes back. The message was not received properly. Send it again. He resets the Lorenz system to the same start he has just used and begins typing the report a second time. This time his fingers take shortcuts. The words still make sense to the intended recipient, but they no longer occupy the same character positions as the first version. That human shortcut is what changed the cryptographic problem. Tony Sale's account gives the famous opening example. The first text began with Sprachnummer, meaning message number. On the retransmission, the operator shortened it to Pichspruchenar. The abbreviation conveyed the same meaning to a German reader, but it changed the alignment of the text almost immediately. Other abbreviations, corrections, and altered punctuation followed. Tiltman's own account says the two versions contained wrong keys and correction passages, producing increasing offsets until the difference reached roughly 500 letters near the end. The Bill Tutte Memorial Fund summarizes the result more simply. The second message was similar, abbreviated in places and shorter. This is the part that popular retellings often compress into "he reused the key." Reusing the key created the dangerous condition. Rewriting the message made that condition exploitable on a scale large enough to matter. Had the operator copied every character identically, Britain would have received two identical ciphertexts. Comparing them would simply confirm that the same stream had been used. There would have been no rich mismatch to pull apart, and no pair of shifting German sentences feeding clues into each other. The receiver's request sounded routine. For Bletchley Park, it created an accidental experiment. Same cipher stream, nearly the same German text, thousands of characters long. The 12-letter indicator is the center of the mistake. The Bill Tutte Memorial Fund records it as HQI BPE XZMUG. It told the operators how to establish the Lorenz start for that transmission. Seeing the same indicator on both messages told the British that the machine had been returned to the same starting state. With an additive cipher, that is a dangerous reuse. Write the first ciphertext as plain text A plus key K. Write the second as plain text B plus the same K. Combine the ciphertexts using the same addition rule, and K cancels itself. What remains is A plus B, a direct mathematical 5 relationship between the two German texts. The British do not need to know K to make it disappear from that comparison. The reused setting performs that cancellation for them. That still sounds easier than it was. A plus B is not plain text. It is two unknown messages tangled together. If A and B are unrelated, there may be countless plausible ways to split the result. Tiltman had already thought about this weakness and had seen other depths without obtaining a complete solution. Here, the near duplication changed the odds. Both texts started from the same report. When an expected phrase fitted one version, the corresponding characters on the other side often produced readable German too. Once enough of the paired text emerged, the rest could extended like a zipper, with language in one message constraining the other. There is an important resistance point here. Lorenz did not collapse because its engineers built a toy cipher. Under disciplined use, the reused stream condition should not have existed. The machine also produced structured, pseudo-random key rather than a truly random one-time pad, and that structure would later matter enormously. But Britain first needed enough clean key material to discover that structure. The operator supplied it. After Tiltman recovered the two plain texts, one more addition gave him the generated key stream itself. Plain text, combined with its ciphertext, reveals the stream that covered it. For the first time, Bletchley Park had a long specimen of the secret output from the unknown German machine. The Germans had accidentally exposed not just what one message said, but what their cipher generator had emitted character by character. That was a much more valuable object. Getting the two transmissions into British hands was its own technical process. The German Signal was radio teleprinter traffic, the strange non-Morse sound that British Y station operators nicknamed new music. The impulses could not simply be listened to and written down like Morse. They had to be recorded accurately, converted into characters, and sent onward for analysis. Directional transmitters, changing frequencies, and weak reception made that collection problem harder than the neat diagrams in museums suggest. Modern museum displays usually tell this part of the Tunny story through Knockholt in Kent, which became the dedicated British intercept center for German high command teleprinter traffic. There is a wrinkle in the 1941 chronology. Historical accounts of the earliest Tunny intercepts place them at the Metropolitan Police Y station at Denmark Hill in South London, while later Tunny interception was concentrated at Knockholt. The safest reading of the surviving accounts is that British Y service operators captured the August depth inside that evolving intercept network, with Knockholt soon becoming the specialized hub. The later Knockholt workflow shows why accuracy mattered so much. Tunny was a 5-channel system, so one missed mark or space changed a whole character and could disrupt the statistical relationships the codebreakers were testing. Radio receivers fed undulators, pen recorders that drew the incoming mark and space pattern onto paper slip. Slip readers interpreted that trace and perforated standard teleprinter tape. The encrypted data could then travel to Bletchley Park over General Post Office landlines. A single bad character 6 could spoil cryptanalytic work far downstream, so the intercept process became an industrial discipline of checking and duplication. For the August 1941 pair, the first obvious clue was procedural rather than linguistic. Both transmissions carried the same 12-letter indicator. That made the pair worth urgent attention. They reached the research section, where Tiltman already understood the Vernam-style additive principle behind this class of teleprinter cipher. Notice the chain of accidents and competences. A German receiver asks for a repeat. A sender violates the start setting rule. The sender then abbreviates and edits while retyping. British interceptors preserve both streams well enough to recognize the repeated indicator. A cryptanalyst knows exactly what a depth might permit. That last step is easy to underestimate. Thousands of intercepted groups have no value if nobody recognizes the procedural fingerprint inside them. Remove any one of those links and the story changes. The radio error alone did not break Lorenz. The British success came from recognizing what kind of error had occurred and preserving enough signateldeed to exploit it. At Bletchley Park, John Tiltman faced some of 2 unknown German texts. His advantage was that he knew how military German behaved. Standard phrases, unit designations, and predictable administrative wording could be tested as cribs. Military traffic was not free-form literature. It contained conventions, repeated formulations, numbers, ranks, and unit labels that gave an experienced linguist anchors. If a guessed phrase was placed in the right position on one side, the mathematical relationship immediately produced candidate letters on the other. If those letters formed plausible German confidence rows. If they produced garbage, the guess moved. Bletchley Park, 1941. Tiltman works through printed teleprinter groups and pencil calculations. He tests German he expects to find, rejects combinations that produce nonsense, and keeps the ones that make readable language emerge on both sides. A word recovered in one message gives leverage against the second. The second then gives leverage back against the first. The Bill Tutte Memorial Fund describes examples such as Roem 1, Roman 1, a form expected in German Army unit references. When the placement was right, the paired output yielded further meaningful German. This was not brute force over the astronomical space of Lorenz settings. It was disciplined depth reading, using language to separate 2 texts whose key stream had already canceled. According to the National Museum of Computing, Tiltman completed the handbrake in about 10 days. The result was extraordinary. Nearly 4,000 characters of key material derived from a machine whose internal mechanism remained unknown. That key stream was far more diagnostic than a single plain text because it was the direct output of the cipher generator itself. And this is where a second misconception needs correcting. Recovering the message did not mean Lorenz itself had been solved. Tiltman could tell what key stream had been generated for this transmission, but not how the machine generated it. Several people looked for a pattern 7. The key was handed to Bill Tutte, a young Cambridge chemistry graduate in Bletchley Park's research section. Tiltman's brake opened a door, but the room behind it was still dark. Years later, Tiltman gave the counterfactual in unusually strong terms. In a 1960 account preserved by the NSA, he said that as far as he could discover, the machine could never have been solved without the isolog depth of the 30th of August 1941. That is not a measurable estimate in weeks or months. It is the judgment of the man who made the first break that the opportunity may have been unique. Tutte received a long string of key symbols and a question. What kind of machine could produce this? He had no wiring diagram, no captured rotor, no manual, and no photograph. He had output. He began by writing the 5 teleprinter channels separately and looking for repetition at different periods. This meant pages of hand analysis, not a machine search. The key was turned into rows, shifted, rewritten, and compared until regularity appeared. The Bill Tutte Memorial Fund records a revealing false start. Tutte found a repetition at 574 characters, but a cipher wheel with 574 positions seemed implausible. He factored the number. 41 was a factor. When he wrote the key on a period of 41, a pattern appeared strongly enough to suggest a wheel with 41 positions. That became the first chi wheel. His next major deduction was a second periodic component with 43 positions associated with the psi system. Those 2 footholds gave the research section a way to attack the rest. Over the following months, the team reconstructed the logical architecture of a 12-wheel cipher attachment without seeing the German device. Later captured machines confirmed the central deductions. The British learned that 5 chi wheels stepped regularly, 5 psi wheels moved irregularly, and 2 motor wheels controlled that irregular motion. The machine had left its fingerprint in the key stream. This is the main turn in the story. The August mistake did not simply leak one report. It produced enough structured output for Tutte to move from cryptanalysis of a message to reverse engineering of a mechanism. Once the mechanism was understood, the problem changed. Bletchley Park could build its own logical equivalent called Tunny to turn recovered settings and ciphertext back into German. The remaining bottleneck was finding the changing wheel patterns and start positions fast enough for intelligence to remain useful. That bottleneck was severe. Tony Sale's history notes that early hand methods could take 4 to 6 weeks to find settings for a message. A strategic decrypt that arrives a month late may be historically interesting and operationally worthless. The path now pointed toward mechanization. The mistake of 1941 had exposed the machine's logic. The next problem was speed. By 1942, British engineers had built Tunny machines that emulated the Lorenz logic Tutte's team had inferred. In 1943, Max Newman's section pushed further with Heath Robinson, a 8 machine designed to automate statistical attacks on the chi wheel settings. It worked, but 2 high-speed paper tapes had to remain synchronized, and they often did not. Tommy Flowers at the Post Office Research Station proposed a more radical answer. Instead of reading both the intercepted message and the simulated wheel patterns from separate tapes, his machine generated the wheel patterns electronically. The result was Colossus. The first machine used about 1,500 valves. The National Museum of Computing records its first attack on a Lorenz message at Bletchley Park on the 5th of February 1944. Later Mark II machines used about 2,500 valves and could read roughly 5,000 characters per second. By the end of the war, 10 Colossi were operating, and the museum credits the wider Tunny operation with decrypting tens of millions of characters of high-grade German traffic. None of that means one radio operator invented the computer by making a mistake. The mathematics, engineering, and organization required years of work by many people. The causal link is narrower and more defensible. The August 1941 depth supplied the long key stream that let Tutte reconstruct Lorenz, and that reconstruction created the technical problem that Heath Robinson and Colossus were built to attack. So how much longer would Lorenz have remained opaque if the retransmission had been made by the book? There is no honest number. The strongest evidence points away from a few more weeks. Tiltman himself later said he could not see how the machine would have been solved without that particular depth, and NSA historical material notes that German procedure improved soon afterward, with no later depth of comparable value for reconstructing the whole machine. The mistake was tiny at the keyboard and enormous in consequence because it exposed a reusable structure at exactly the moment British cryptanalysts were prepared to recognize it. A repeated setting let Britain read the logic of a secret system. 3 years later, Britain used radio trust itself as the weapon. The next story is Garbo, Day, and the German messages that were believed precisely because the deception had been built to look reliable.